So my name is Seth. I work at Microsoft. I work in the AI space. And what I want to talk about is I want to talk about LLM theory to practical agentic implementations. And what this means is very fancy sounding, but what it means is I think we are abstracting some of this stuff incorrectly. To the point where when we use AI, we kind of think it's this other thing that doesn't involve us as programmers. I'm a developer. And so what I'm going to show you today is I'm going to show you what the actual primitives are, how you use them, and then finally how you can compose them. Does that make sense? And once you have that fundamental understanding and feeling of what an LLM can do, all of a sudden you're going to be like, oh, I can put this here. I can put this here. I can put this here. Whereas right now it kind of feels like there's like 4 apps that do AI correctly, even if that, and then one of them might be at Microsoft. Do you see what I'm saying? And so that's what I want to talk about today. Is I want to talk about the agentic primitives and how you understand it. My background is in machine learning. I was doing machine learning before it was cool for a long time, and so this stuff is actually near and dear to my heart. It's very good stuff. If you want to get this is just a repo. I'm just going to go through. Let me show you the pattern. I'm going to talk about how LLMs work, how they're trained briefly, because you probably don't want to get into the math. I love the math. It's kind of cool. But then I'm going to go through 9 scenarios that get progressively more complex to show you not this is how you should do it, but to show you like when you start with the right primitives, you can start to do other things. And the reality is that the best AI tools, the reason why they're the best is because obviously they have good models, but you can have a terribly good model in a crappy harness and do stupid things with it. And so that's what we're going to talk about today. And again, there's not like 1,000 of us, so you can be like, hold on, what is that? I want to see the code. So let's start first with, and I'm going to go fast because there's a lot of stuff. Let's talk about how LLMs work. LLMs are this giant machine learning algorithm that's designed to predict the next token. And by token, I mean a piece of a word. Because like if the LLM had to reason about all the words in a vocabulary, it's too much. And so it splits words up in a really smart way into things called tokens. Tokens are this giant vector that represents a word in hyperdimensional space. That's the math I'm going to tell you. And so when you're actually using an LLM, what you're doing is you're passing in a collection of tokens, and then it's like, I think the next one is this one. Boop. That's all it does. And you're probably thinking, well, Seth, that's not what I see it doing. No, it's because what it's doing is it's doing it in a loop. And so it gets the token, right? And then it spits the next one out in like sort of this kind of fashion, right? So it's like, hey, the best food in Japan is sushi. And then you feed it back into the model. The best food in Japan is sushi, comma. That's the token. The best food in Japan is sushi, comma. Ramen. You see what I'm saying? That's what this is doing. That's why when you look at it, it looks like it's typing. It's not typing. It has no feelings. It has nothing. It's a bunch of math. Like, if you saw the math, it's basically all linear algebra and calculus, nothing else, right? There's some fancy things with the sigmoids, to smash things in the middle, but that's it. And so that's all this thing is doing. That is the fundamental unit of a large language model. Hopefully, this is probably surprising to you, but also not. And that's how you know it's true, right? So these things are giant next token predictors. That's all they do. And what happened is early on, when they saw this, they're like, oh, this is kind of novel. I wonder if we can make them better. How do we train these things? So the training part is quite simple. So for training, math is super cool. And in other places of the world, they have more than one, like in the UK. In Canada, do they have maths here? We just have the one in North America. So what's cool about this is because like this model is just a giant math function, and you give it a collection of tokens, it produces an output. And it's not just a single token, because I kind of lied. It's like all of the tokens with a probability of, is this the right one? Right? So all the tokens, and then there's a number. What's the probability? The numbers are super tiny, right? And so, for example, when you change the temperature, you know how it's like, if you change the temperature of the model, it makes it more creative. That's stupid. It basically warps the probability distribution so other tokens are also more likely. You see that? It's not more creative, it's just maths. And so what happens is when you do this, when you have a stupid model that doesn't work, what you do is you pass some tokens through it, You know the text that comes next, but you're like, I know what it is supposed to come next. What do you think comes next? And so it has this giant output vector of all the probabilities, right? And then we have the other one, which is the right answer, which has a 1 in one of the slots, right? And now that we have these two mathy things, we can subtract them and see what's called a loss. And if the loss is 0, that means it got it exactly right. Good job. If the loss is non-zero, then it made a mistake. And so because calculus is wonderful, you can do crazy things like subtract them and square them. And then you get a loss function, and that loss function you can optimize with calculus. And so effectively, you're pushing tokens through this whole thing. Out comes an answer. You check, did it make a mistake? You push it back, and because calculus is wonderful, that when you optimize a function, you take the first derivative set equal to 0, right? And calculus with functions composes down, right? Derivative of an outer function is the derivative of the inner function times the out. You see that it goes down? So basically what happens is when you subtract these two things and it gets it wrong, all it does is it literally just goes back and updates all the weights back based upon that loss. And it does this over the internet. And those are why the best models do a good job. That's it. That's it. Sorry. But intuitively, as you hear this, you're like, that's surprisingly simple. And yet, it makes sense. That's why when you're, for example, fine-tuning a model, you're basically updating its weights with your own data. When you're distilling a model, you're getting a smarter model to produce the right answers so that the smaller model can learn from the right answers by subtracting, and then, it's that kind of thing. So those are how LLMs get trained. So what happened is early on, when people saw this, I think it was GPT-2 era, GPT-3, people were like, wow, I can give it text and it produces the next likely tokens. So you can still do that. They're called completions, but the model isn't there. They're all chat APIs now. But you used to have this API called completions where you would say, finish the next set of text, right? And so I'm going to be using a library that I wrote called Prompty, which is super nice because it embeds the prompt and the settings for the models in the same place, and it allows me to run it interactively so you can see exactly what's happening. Does that make sense? So that's what I'm doing. The app we're going to be doing is this app called Draft Flow, because now we have the 9 scenarios that I'm going to talk about. These are them. The 9 scenarios we're going to talk about. And Draft Flow is an application that helps me draft copy because I hate writing stuff. I'm more of like a stream of consciousness bullet kind of guy. And so I want an application that would help me write my things a little bit better. And so this is a stripped down version of that called Draft Flow, just to show each of these examples and how it gets progressively better. Does that make sense? Cool. So this is all available in a repo. I just made it public like yesterday, like 5 seconds ago. If you go to github.com, Seth Juarez Draft Flow, you'll find it all in there. You can totally get it if you want to take that picture. Just think of like a draft flowing from your LLM. Also, I hate slides, so I wrote tooling to build slides for me. And so when you see these things, these are slides that are made for me. They're actually in the app. So you can, when you run it, and it's using Aspire, so you can just do Aspire run, and it will run, okay? You have to give it your own model keys. Sorry. I can't give you everything, So let's get started. So let's start first with the simple one. Now that we have this model where like I can give it stuff and stuff comes out, let's test it, right? So I'm going to test it by saying, hey, write a concise launch copy for Draft Flow Workflow Builder, audience support, blah, blah, blah. So this is me just treating it like a dumb completion. So all that's happening is it's going to say, okay, I am going to write this for you. And it did. And that's what it wrote for me. It's pretty dumb. It doesn't do anything. If I say something like, hey, make it better, what is it going to do? It's not going to do anything because it doesn't know anything. I'm treating it like I give you a collection of tokens. You give me a collection of tokens until you think you should stop. That's the lowest primitive, remember? And so when I say, hey, when I say something like, hey, write this thing, it does this, and I'm like, hey, make it better, it's like, make what better? Because it turns out that these models are stateless. even in between each token. As it's typing to you, it could switch machines, right? Because all it's doing is it's taking a collection of tokens and predicting the next one, and then it's putting it back into the queue and then doing it again like a typewriter, like old school, right? And so when I'm doing this, when I'm using this in regular old school completion mode, every time I tell it something, that's the only thing it knows about in the universe. Do you see that? Is this a good use of an LLM? It could be, actually. Early on, here, hear me out. In the days of GPT-3.5 Turbo, we would use something called intent mapping to do code branch. For example, we would have a completion. A user would be like, I'm so pissed off, nothing is working. That sounds like a support question. Where can I get new boots? That sounds like a sales question. So you could put those phrases into something like this and say, when you see this, you need to predict whether it's support or sales. And then you branch. Do you see that? So is it useful to still use this? Sure. Absolutely. Here's another stupid idea. On your blog, now, you want people to comment, but you want it to not be spicy. You could do a completion that says approved or not approved and why. Done. But because everyone has forced us into this, we need to use LLMs the other way, we kind of lose this abstraction that happens to be quite useful. Right? It's effectively semantic narrowing for you to be able to do control flow decision. Does that make sense? And that's okay. You should do it. We did it all the time. It's called intent mapping. But again, what happened is the industry started abstracting higher and higher, and so now we lost this, which is actually quite useful. So that's a simple one. Let's take a look at the actual. Here's the back end in API. This is the prompt file. Notice that the prompt file has a front matter, and then it has a system message. You are draft flow in mode 1. Return only markdown text for the editor, and this is the user's command. Does that make sense? And if you look at it, you can actually see you are draft flow mode 1, write a concise launch, right? Because this is what it's putting into the values. You can actually see all the front matter, right? For example, it's using Foundry GPT-4.1. It's using a certain way of templatizing. And then when you run it, you're going to see that it's just going to run the thing on its own because it has enough, and it's going to give you the output, and you can see the output is this thing, which you saw before, but you can actually trace through and see what it ran, right? Because this prompt thing is nice because it injects things into the holes, it parses it into the array, and then it executes it, and you can see here's the answer. And I'm just using this, right? And the cool thing about this kind of code is it's kind of stupid, right? You load the file and you invoke it, and that's it. Does that make sense? So that is simple mode 1. And you saw how when I did simple mode 1, and I tried to talk to it some more, it was stupid. That's because we've forced LLMs into a chat box, which is kind of dumb. It does so much more stuff, right? Imagine something that can complete your thought. How would you use that? There's many other ways other than just a chat box. But I put it in a chat box because, again, here we are. All right, so let's take a look at the explanation. The prompt file goes in, system of the user prompt, the thing predicts tokens, and then that's the output. Super simple. Okay, good? Questions? Okay, mode number 2. They discovered early on that you could actually force the output to be a certain way, right? So instead of having like output just be straightforward text, you could maybe force the output to be JSON, right? So now if we can give it a thing and force it to have an output of JSON, then you could do a bunch of other things. Like, for example, notice that when I did my thing last time, it just spit out this thing. But now what I'm going to do is I'm going to give it some structured output and say, I want you to return JSON for you to tell me something, create a title, and write the thing. You see that? But as a developer, because I'm getting not just text, I'm getting JSON back, I can do this. It's like, oh, here's a clear, friendly launch guide. And notice that even in simple structured mode, you're getting some pretty good stuff. This is starting to look smart. If I were to tell it to do what if I do this? I don't think I have a thread in there. Can you make it better? Let's see. Hopefully I wired this right. What do you think is going to happen? It knows nothing about the universe again, right? Even though it looked kind of smart. And so you can use LLMs in this mode too to do some clever things, right? And so it didn't know anything here because obviously it was dumb. If I go back to the code, you're going to see in mode 2 structured, the only thing that's different really is that it has some inputs and then it has some outputs. And the outputs tell my runtime, I want a structured output, and your model needs to support it, otherwise it will throw an exception, and it will return well-formatted JSON that then the runtime parses into a dictionary, or in C# into an object. Do you see that? And so notice that even with this primitive, there's a ton of stuff you can do, right? For example, there's been situations where if there is a good enough DSL, you can actually tell it to render a diagram in one shot. Right? Because you can give it the structured output of what the DSL looks like in JSON and say, I want you to make a diagram that's it hits a fit, and then boom, output. This is early on in the days, this is when they had it output like websites. And you were like, wow, this is crazy. Well, not really. It's just structured output. And that's good, right? Okay. So now let's talk about, by the way, is this an agent? This is where people get screwed up. Because the question I have for you, and this is, you're gonna want to say the wrong thing, which is going to be right. Do the models have agency? They do not. The only agency they possess is to predict the next token. It's the runtime that uses those models that imbues that output with agency. And the only agency you can imbue it with is branching. That's it. Does that make sense? Branching. And you'll see that the branching becomes even more complex. So in the first mode, notice that it was not agentic at all. In the second mode, kind of agentic, because we're telling it to put stuff in different parts of our app. If you are deciding based upon the output with your runtime to branch, you are imbuing that model with agency. And it's the runtime that does it, not the model. This is super important. The model only has the agency to produce the next likely token. It is the runtime that allows those tokens to produce branching. Okay, so that was model number 2. The code is basically the same. Let me move this over here. You can see it loads it up, it structures, it invokes it, but notice that it gets the structured payload into a dictionary, and then that's it. By the way, this code is not hard. You see what I'm saying? It's not hard. It's pretty stupid. It's not stupid. It's very stupid code. It's not even like, it's like, hey, Seth, you just wrote a while loop. Congratulations. Yeah, but it's a different kind of control structure now, right? Which is what you think about it. It's both a control structure and a data structure at the same time. It's a weird kind of. Okay, should we go to mode 3? How are we doing? Oh, good. Now let's talk about the full chat. Oh, did I show mode 3 explanation? Okay, here we go. So here's the raw output tokens first, the type JSON that it produces, and then the app uses the fields. Right, so that's pretty much what happens on mode 3. By the way, is this a useful way to show this stuff? I find slides tedious. You know what I'm saying? It's like right here, I can just click buttons and, okay, good. I love it. It's the first time I've done this, by the way. It took forever to get this to work. Oh, huh? Oh, good. Okay, let's talk about the next step, this notion of threads. If the LLM decided, like, hey, we need these things, I'm out of the camera. We need these things to remember and keep context of what's going on. So this concept of a thread was born. Or a messages array is another thing. So that anytime, like I said something, it would store it in the array, and it said something, it'd store it in the array, and then boop, boop, and then this data structure called the thread was born, so that it would keep the context. Does that make sense? Okay, so let me show you what this looks like in my code that makes it simpler. you'll notice that it has this thread object, right? And this thread object effectively is an input thread, and you can see that it has like an example. So let's actually run this so you can see what this looks like. Notice that it's starting to thread, and it's like, hey, here's this thing. Make it longer, please. Now, is it going to be able to make it longer, please? Yeah, because it has this data structure that keeps getting passed to itself. So it knows what it is, and if you've studied it or NLP, I studied NLP before it was popular. It is what's called a pleonastic word. That's like a $5 word, even in Canadian dollars. Pleonastic, right? Which means it could refer to anything. And that's hard, but notice that LLMs don't care about pleonasticity. That's a $15 word. It just does the thing, right? Because what's happening here, let me stop this so you can actually see the whole session, is that for every turn that it has, it sort of passes the thread of what's been going on. Do you see that? So before turn 2, this is what it's being passed in, and so it gets that into its context. And what does context mean in this case? Into its, like the tokens before it gets passed in with its prompt or whatever space. By the way, is that an infinite space? No, it is not. Also, if you think having a longer context is better, it isn't, right? I actually found that whatever you put last and it's in the user role actually gets paid attention to the most, just FYI. So I usually, sometimes when I make demos, I make demos at Microsoft and I show them on stage, and everyone else doesn't like, we can't show this demo live. We don't know what the LLM is going to do. I'm like, I do. I'm going to put it in the user message. And it works almost every time. Yes, sir?
Does it cost you to get all that repassed every time?
Yes. However, if you want to get into fundamentals, there is this caching layer that happens for the tokens, so that, because what happens at the lowest level when you're putting it in, it goes through this transformer layer where it needs to do like 3 matrix multiplications that are huge. But if you don't change stuff from before, it uses cache. That's why you don't change stuff at the top of your prompt. Does that make sense? It's pretty clever, right? Now it's like, oh, this sounds like computer science. Yeah, exactly. So,
if you change stuff at first, wouldn't it just invalidate the entire cache?
yeah, you just got to do it again. Yeah, and then you just do it again. It will work, but it won't be as fast. Okay. And by the way, like, you could heat several cities, you know, sometimes with some of the stuff that we're doing with the, like, you should try to use your cache. Okay, so let's see what this looks like in the actual code. So what are we, mode 3? Mode 3, I hate when these. Mode 3 is like, hey, instead of just execute, it produces a turn. And what you're seeing is like, well, how does it keep knowing what's in there? In the chat request, you can see it has the thread. So again, there's a boundary between the backend fast API and front-end React. So when it gets an answer, it just stores it, and then it sends the thread back. So there's this portable thread that's going back and forth. So now I'm going to be like, hey, let's shape launch copy for our draft flow, blah.
Before you do that, where was the cache? I didn't see that.
The cache, what do you mean, the thread?
No, I saw the thread.
Yeah.
That's the cache.
Yeah, so okay. So it's storing it here in the React side.
Oh,
And so that's, like, you can see it literally stored right here.
Yep.
And then it just sends it back. But again, that is an implementation detail. You can do this any way you want. Okay. Maker it longer and poetic. Now, you're going to see that because it has context, it's like, oh, okay, I will do it. And now I think it made it into like Shakespeare. Step into a new era of effortless creation with Draftflow Workflow Builder. A canvas where you're is stupid. It does whatever you tell it to. Sorry, I meant limerick. I said lamerick, unfortunately, because I'm terrible at spelling, but it doesn't care, right? And so now notice that I have a thread context that gets passed around as a separate object. Make sense? We are not going to cover, because by the way, the longer you talk to these things, the dumber they get. Remember early on, people were like, wow, the LLM was just telling me the weirdest things. I'm like, yeah, bro, What'd you put in its context? It's more of a reflection of you. Right? Remember early day? Like it's telling me it's alive. Yeah, you made it think that, dummy. Of course it is. Right? And unfortunately, some of us in our technical field encourage this kind of stupidity. Let's go to explain here and show you that a message comes in, thread object, it gets bigger, that is passed in as context to the model, and then it keeps going, keeps going, keeps going. By the way, when it renders out, it actually just puts them into tokens, and like the user and assistant message are tokens, actual tokens. So it's trained on this. But it counts as its own word, right, as boundary. It was pretty cool. Okay. Okay, questions on mode 3. Okay, now we're going to start to get, by the way, is this agentic? Not really. Is it deciding how your program is going to branch? Not really. It's kind of a toy. Remember, this was a toy when it came out, GPT-3.5 Turbo. We're like, oh, I can talk to it. It's only now on the next step where it became really agentic. So remember we talked about structured output. And remember that the structured output one allowed the LLM to produce adjacent output. Someone had a super clever idea. What if we shape the adjacent output to look like a function with parameters and values? It's clever, right? And what if, as we're going through this loop of chats, right, if I return this thing as a JSON that looks like a function, but I mark it in a special way. I mark it as a tool call. Now, the runtime can take that shape and decide to execute it. Put it back on the thread with the response. This is where things got crazy. No, prompt injection becomes a thing all the time. I'm going to break something with prompt injection in a second, just to show you. But yes. But do you see the thinking now? That's when it really becomes agentic, because it's not just branching like on a word or a piece of a structured output. It's branching into code execution. And that's why when people talk about, well, these things are running amok, I'm like, no, whoever wrote your runtime is an idiot. All the LLM does is suggest the code you should run, or a function. You decide as the runtime owner, as the harness owner, do I execute it or not? Right? So let me show you what this looks like. I'm going to put it in a loop. I'm going to put this in a loop. And so what I'm going to do is now I'm going to say, hey, in a turn, run, while you have tool calls, execute them, put them back on the thread. If you don't have a tool call, I'm done, out. Let me explain this a little bit. Oh, no, that's not. I'm on mode 5. Explain. So here's the thread, right? I give it to the LLM. The LLM might say, I want to run a function. And it does it. We can decide to run it or not. This gets put back on the thread, and it goes back again. And it will do this while there's still tool calls until it has no more tool calls, and it produces an answer. Does that make sense? This is called the agentic loop. It is the fundamental unit of agency for these things. Fundamental unit. And notice that it's born of the first two, right? Like the natural pattern, like this realization of, aha, I can make structured output look like a function, is genius, right? So what I'm going to do is I'm going to give this thing a couple of tools, just 3. One of them is fetch.
It's only deciding to do the tool call because that's the most likely thing.
Correct. It's the most likely thing to do next. So fetch, and then I've changed like how it like sets parts of the app up. I made a tool call to set the title and to set the content. so that it can do that independently and be on its thread as something that was executed. See that? Okay, so now we're going to say, hey, what happened? Okay. I'm going to say, hey, I want you to fetch Azure Foundry. What is Foundry? Then you set blah, blah, blah. And so now I'm going to run it. And so you're going to see things happening a little bit different. And so now when it's like you see these thinking, it's not thinking. It's like, oh, I want to do a fetch. Here's the fetch result. Here's the set title. Here you go. Do you see that? It's doing this in a loop. Does that make sense? So it's just like a little loop. By the way, this is burned into the app or into my runtime so that it's called an agentic loop. So it's a while loop, while not tool call. Or while tool call, I guess. While tool call, execute tool, put it on the thread, done. And notice that it did a good job. Like, not only that, did it put anything in there for, yeah, here you go. Inspired by enterprise-ready solutions like Microsoft. It actually did the fetch. These are real things that it's running. Let's go to the code so you can see what that looks like. What are we in mode? What are we mode? Mode 4. Here are let's see if it did it, if it modeled the tool calls correctly. So here's the inputs, here's the thread, and here's the tools, right? You can see these are the tools that it's going to map to. And each of these things has their own parameters and bindings. So if you go over here, you can see it has a fetch tool. Here are the parameters that it can have, a kind string. You see that? And so this is part of now calling these things. You can set these as the API call out to the LLM, and it will return tool calls for you. Okay, so let me show you the code. So in the service, you can see it loads it. It binds the tools, like so. It's gonna the fetch URL. Notice it's actually fetching it and converting it to Markdown. You can see that right there. And then these are other ones are like I think these are bindings to send information back to the UI. And so it binds them, and then it produces a turn. And a turn, in this case, is a agentic loop. Cool? Okay, again, here's the problem, though. Remember, I still have not, and I'm not going to get into it this session because we're already, halfway through. There's still this notion of compaction, being good about managing your prompt context, et cetera. And so we should make another session for that. Okay, questions about this particular approach? It's good, right? This fundamental loop you can use to solve problems. Like, for example, anytime there is an impedance mismatch between stated outcome and what your code actually does, you can use this as a bridge. Does that make sense? Yeah.
Does the name of the tool, is that just like a token that LLM comes up with?
No. You have to actually give it. Here, I'll show you. Let me go back. That's a great question. So when I'm actually in this thing, as part of the description of this particular execution, these are the tools that I give it. And so here, let me bring up another OpenAI tool definition and call. Here we go, function calling. There you go. You see that? So this is exactly, developer says this, what's the weather, calls gets the weather, execute code, whatever. You can see that you actually have to, as part of the call, you have to give it this JSON thing. And then here's the call that you literally point to OpenAI. You're like, well, why didn't you just show it? Yes. Okay.
What I don't understand is that you give it that name, just like if I am making a time code and it's going to fix my time code, why doesn't it change the name of the main function?
It sometimes does mess up the function name, and that's okay. But in general, they're actually pretty good. Who's calling me? So what happens is when you get here, let me actually show you a full trace so that you can see what's happening. Because I understand the dilemma now. Okay, so there's a thread in here. So I'm going to open this up, and I'm going to say, make me an article. Here, let me just copy the exact prompt that we had in data flow. Reset this. and we'll go over here. So, because I want you to see the exact trace of what happens. So now it's running the agent. And now notice, I need to colorize this better. It's asking for a fetch. Now, because in the extension it doesn't have access to the functions, I got to pretend that so the extension's like, hey, let's pretend this is running. What do you get back? People like cheese a lot, right? And so that's what the article is returning. And so now it's going to set title, cheesy people. And then it's going to process the set title. Then it's going to process set result, more cheesiness. And so notice that, there you go. And sorry, the coloring's wrong. I need to fix the extension, right? But what's happening is, it's the LLM as it's executing in the runtime. What it will do is it's like, here is a function, and the runtime needs to take that, parse those values, find the mapping to the right function, execute it, and put that back onto the thread. Okay? So what you just saw that happened right here. So I'm going to stop this so you can see the actual full execution of this thing. There was a couple of turns, right? One of them was a fetch call that returned people like cheese a lot. And then another one was a set title, but you can see there's parts where the LLM has to make decisions about what to do. And in this case, the decision on this one, let me see here, is to execute this tool. These are the tools that are in there. Okay? So as this thing is running, the LLM just returns this is a tool, run this, you run it, and then it put it back on the thread. Yes?
In your first example, you were getting some information about some Microsoft project, and you said fetch, and that must have gotten translated into a Python requests call.
Yes.
Where did that mapping from fetch to requests?
Great question. So this is happening in my particular service. So this is mode 3. We're in mode 4. Okay, here. Bind the prompt functions to the actual methods. So that's where the binding actually happens. And in this case, if you want to see what the fetch tool does, this is the actual fetch tool. It maps it. Now, if you want to get into the actual, well, let's look at the actual definition of the code, right? You can actually see that as we go down into this, well, there's a lot going on here. You can see while true, there's more stuff here because there's a lot more going on in this tool call loop because there's other things that I'm going to show later. But you can see that it gets the response. There's more tool. There it is. If there is a tool message, it will try to run that tool. If it has tool calls, if it doesn't break, otherwise, tool messages, extend, there you go. So these are the responses that it gets from the actual tools. But this loop is a lot more because there's a bunch of other concepts that I haven't explained yet. So yes, it looks at that JSON. The response that comes back here, let me actually, because I can see the confusion, and I want to make sure that I can probably make this only, we're in 4, right? I am going to do this. I'm going to, just for this, I'm going to take out a thread. I'm going to take out the thread and just run it. Let's see if it works. Good. So I just ran the one call. Notice that the output is effectively run this tool fetch with this argument. That's that was one crank of the LLM. The runtime says, okay, run it. And then it puts it back on the thread. See that? Okay. I need to undo that because it will break my demo. So Control Z, Control Z. It turns out that when you run, in the extension, if there's a thread in there, it knows you want to talk to it. But I took that thread out. So it's like, oh, you just execute, fine. Here's your output. Run this function. Does that help? Is that clear? Cool. Okay. Yeah. Yes. Correct. And that's what the binding is for. The binding says, hey, if you see this here, let me go to the code for binding tools. Effectively, it just puts all of those function, because they're objects. What's your preferred programming language? C++, C#? Okay, so it'd be a function pointer that's mapped to that string. Or it'd be a delegate in C#, for example. Because a delegate is an object representation of a function, right? And so it's basically, this dictionary is like, this name belongs to this delegate function pointer, whatever. And so the runtime, when it gets the name, it like looks it up in its dictionary. Is this a real function? All right, let me execute it. Okay, does that make sense? Okay, cool. Cool, great questions. By the way, these are good questions. Okay, so I put it back, right, so it wouldn't break. Okay, so did I already run this with the tool and everything? Okay, all right, mode 5. Now that we have tools, we can do some cool stuff. And the concept of memory is an interesting one because it's very nuanced and varied. I'm going to show you one way to do memory, but there's multiple ways. All we're trying to do is we're trying to get the right thing into the LLM's context so that the next execution role does the right thing. That's it. And we're trying to do it in a way that saves cost and that makes it as reliable as possible. Does that make sense? So for this example, I made a memory tool so that when I say, hey, remember when I said this thing? I attach use memory as one of its tools, and it uses it to be like, I don't. I'm going to go ask. Do you see that? Okay. So here is this thing. I think this memory loaded up. Not yet, but I'll show you in a second. Use memory before writing, launch copy or draft flow, respect my preferred tone. So I'm going to do this, and what's going to happen is it's going to use memory. Avi, I am user A. It's going to set the title and a thing. You can actually see the memory here. I have user A memory. This is my approved stuff. Okay, there's a user B in there for demonstration purposes. Okay, so it did it, right? Notice that this is one way for me to do memory. There's all kinds of memory. There's something called short-term memory. That's whatever's in its prompt, right? There's episodic memory, which is like, tell me about Seth. What does he like? You know, sometimes if you're using a certain like Claude or some other, it keeps reminding you of this one thing you said like months ago. You're like, shut up and get it out of your memory. That's what it did. It puts that in its memory. About you. That's episodic memory. There's something called procedural memory. Do you know what that is? That's the tool calls that are in its prompt. Like, this is how you do stuff. Do you see that? There's long-term. There's all kinds. Like, if you go to the psychology of memory, there's all kinds of memory. But just like us, but not at all like us, it only has context window length of stuff it can work with. You cannot. That's an engineering fixed fact. Okay. So let's do something here. Let's do something. Hey, silly thought. User B has way better ideas. Can we use their thoughts on this? Should I be able to do this? Oops. Daily. Do you see the problem? Oops. Whose fault is that?
Yours.
That's my fault. Yes. Yes, 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 and yes. Because again, all the LLM suggested I do is run that function with user B's ID. And my runtime just was like, sure. And it put it back on the thread. Do you see the problem? This is stupid me. It's an ID10T error on my part, right? So how do we mitigate this? Well, there's a couple of ways. And this is where the next concept number 6 comes in, this notion of guardrails. Now, what a guardrail is, I did not show you the memory. Memory, honestly, memory is like just a tool call. There's nothing. It's just a tool call, right? So let's go into the guardrails. So what you can do in your runtime is you can create guardrail functions that can look at other functions, right? This is stupid. I mean, honestly, like if you own your own loop, you can like check the function in there. By the way, side rant. This is why I don't like things like MCP servers, right? Because what they do is they pollute your context with all possible tool calls, which makes your LLM dumber. Not only that, you're not managing the agentic boundary between a suggested execution and the actual execution, because MCP manages that. And the first smell I had of that was when I was asked to write an MCP server in FastAPI. I wrote all of my FastAPI stuff, and then I wrote like a couple of functions that just wrapped the FastAPI, and I'm like, why wouldn't I just use FastAPI? We are, after all, just mapping structures that look like function calls. That's why I'm not a fan of MCP personally. It abstracts too high in a way that's not useful, in my opinion. Like, because when you do MCP, it actually responds with all of its tool calls, and now you have that in your procedural context. Is that necessary? Could be, maybe, if you did it right. I think so. But if you're not in control of it, then it's probably wrong. So let's do a policy here, and let me show you what that guardrail looks like in my runtime. So we are in Guardrails here, and if I go to the service, you can see that I have this guardrail check function, and here's the memory guardrail. You can see blocked memory access, tool call reason. You can see there's the bindings, and then I add a guardrail to this thing, and then I run it with the guardrails, right? And I think, let me see what what does my memory guardrail do here? So memory guard, I've used memory, set memory and arguments, does not use, oh, there you go. Easy. If any of these things are being executed and it's not the same user ID, don't run it. Does that make sense? Cool. Let's try it. Okay, for this guardrail demo, try to read user B. By the way, I kind of totally gamed the system here. But what's going to happen is you're going to see, oops, can't do that. Oopsie daisy. Guardrails are cool, right? They can do this. You see that? And so in your own loop, you can do guardrails. But I feel like we can do better than this. Do you want the LLM deciding what the user ID is going to be? How do we fix that? And this is where we go to concept number 7, which is this concept of binding. Binding, right? Because you may have a function call that requires like session ID, user ID, current date. Do you need the LLM to use its intelligence to pick those out? No. So what you can do is you can have these things called bindings on the inputs, because my prompty thing has inputs, and I can bind those inputs into function call members, so that when those function calls are bound to the LLM, it removes those from it ever considering them. And then when I execute them, the bindings tell it what values to inject. Does that make sense? This is kind of... Now what's cool is the LLM doesn't even have to think about the user ID. Why should it? Right, and let me show you what that looks like in terms of bindings here. And I gotta hurry up because I'm running out of time. And like I said, I have to leave when I have to leave. Okay, so here is the here's the inputs. Notice that there is a message, a thread, and a user ID. And notice that in the here's the fetch function, set context. Notice the use memory is like, hey, whenever you do this, bind the input to that user ID, so that when this function is mapped, that property is completely removed. Let me show you what this looks like when it runs. Here, honestly, user B has better approaches to doing things. What do you think it's going to write? Is it going to use user B's or user A's? A's, because it doesn't think about it. So if you look at it, when it uses the memory, it's like, It's just calling use memory. It doesn't know anything because in the runtime, it knows that the input parameter user that is passed in on the turn belongs to that binding, and so the LLM doesn't even have to think about it. And this is stuff you can't do with like MCP. Maybe you can. Maybe they did bindings. This is a newer thing. I don't know if I made this up. Right, but notice that it's actually useful because it uses the principles to do the right thing, to do the bindings. Okay, I'm going to go fast now, and it's going to get more complicated. Now let's talk about this notion of steering. You know how, if you've used GitHub Copilot, you know how you type and it waits and sometimes it sucks things in while it's doing things? Well, it turns out that when you're in this while loop, there's an opportunity at the top of the loop to have this stack of messages that it can drain into the thread. That's called steering. Does that make sense? Because a while loop is one of those things that's like nigh unbreakable, right? It's like the ring of power, must be destroyed in the fires of Mount Doom. But if you thread this thing, right, and it can check a queue of messages, that's called steering. And so when you run this thing, you can here, let me explain it. When it's running in this loop, like before it calls the next time, it's like, is there something in the queue? Boop, 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 and then goes. So let me show you a steering example. This one's a little more complicated. I had to use a socket. Let me go to the socket one so you can see it. Here's the service. There's the here run with steer. No, let me go to the route itself because you'll see it here. So I connect with a socket, right? Because with a socket I can send stuff at it, and it can drain stuff as it goes. So let me do this steering here. So write a copy of the blah, but focus on this and don't forget that and avoid the hype. Notice it's still running its tool. Still running its tool. And now it's like, oh, I found your 3 messages. Let me put them into the thread, and then it's going to do the work. That's how. Have you done this in your Copilot? That's steering.
No, stop it.
Yeah, no, stop. Oh, sorry, I'll stop right now, right? This is what steering is. But notice that it requires a little bit more machinery. Okay, let me stop right here because the next thing is where we get into composition. So thoughts on this stuff. It's pretty simple stuff, right? But once you know it, you kind of can't unsee it. Like anytime you play with this stuff, you're going to think about this, which is great, right? Because once you start using tools that are bad at it, like I'm not to bag on some of our folks, but some of our office copilots are getting way better. But in early days, they were not good, and the reason why is because they didn't use these primitives. Now they are. Now you can before it used to be like, can you edit this Word document? No, sorry, I can't edit Word. What? But give yourself your own tool. Come on. But now they can. And so if you ever see like someone literally just bolting on a chat, it's because they didn't go to these principles. I recently heard Shopify has started to build their own harnesses that do really cool stuff, that know its systems. And for example, how do you get an LLM to know your systems? Well, that's procedural memory. That's tool calling. Okay. Questions about anything so far? Because we've only dealt with using a single prompt structure. Now we're going to move to multiple. Questions? Okay. So now to finish up, we are going to go to this thing called a composition workflow. And what I'm going to do in code is I'm going to have 4 different LLM prompts, 4 promptee files, right? There are 4 different files that each have their own job. However, every single one of them will take a thread. You get what I'm laying down here? So every one of them has the same context. By the way, this is, we got to be careful here because I'm not suggesting that this is the only pattern. This is a pattern that once you understand the primitives, you can use to do cool stuff. So all of these things share one thread. And one is really good at doing research. It puts stuff on its thread, passes control to the draft. It puts things on its thread, does the review, does the title, and then writes the artifacts.
So they're running sequentially?
Yeah. Here, I'll show you. So here are the, here's, what are we, mode 9. Mode 9 here, what's first? Research. here's research, right? You draft 109. This is research step. Here's the thread. What's the next one? Research. I don't even know what draft. Yeah, there you go. Draft. You are draft blah blah. Create a review ready markdown draft from the user request and website research and the workflow, and then title. Create a good title, etc. And so now when I go back and run this, you're going to see context being passed. Like here's the researcher. It's doing the fetch. It's requesting. It's doing the research agent. Now it's passing over to the. Oh, it's done. The runtime now is getting the research context. Do you see that? Like it's passing control flow, but it's maintaining state through the thread. Some of these have tool calls and need their own loop. Some of them don't. And that's okay. But all of them take the thread. Do you see that? So now what I've built is I've built a full agentic system that does stuff in a clever way. Does that make sense? And by the way, this code you can all download it, and you can see it go. It's going to start the research. Starts the research here. It does the fetch. There's the research output. Then the draft agent starts, right? And then it's like, oh, I need some memory. By the way, does it need to know what user ID it is? Nah. We did bindings. Guardrails would have stopped execution. Which is sometimes you need to have that kind of powerful thing. Sometimes guardrails need to stop execution, and that's okay. But in this case, no, it's just like we just did a binding. It passed over the review, did the title, and wrote. And that's the full sort of end-to-end. Let me show you a better explanation with Mermaid here. Mermaid diagrams are notoriously ugly. Sorry, Mermaid. Notice that it had the starter one. It did the full agent turn on the research. It did a single call on a draft, right? Then it did another turn on the review with memory. And then it produced the title. And then it returned the right. Do you see that? Yes?
So the idea of running multiple sequentially would be looking each one's context more focused.
Yes. Well, remember, it gets the full thread context, but its instructions are more specific. Yes.
Okay.
Not only that, here's what will explode your head. In Prompty, you can have what's called a Prompty tool. So it can decide to call another LLM. That's called implicit orchestration via tool call. This is called sequential orchestration. You can have other orchestrations like where one of the LLMs says sales or support and it branches. And then you do other calls. Some of these might have agent loops. Some of them might not. That's okay. And that's the powerfulness of this. Does that make sense? Okay, now in the last minute or two, to finish up, there's a ton of stuff I didn't go over. Like, for example, the intelligent compaction. If you talk to these things long enough, you'll see it does what's called a compaction. What do you do with all that context? Well, you have to either compact it, shuttle it out to memory, or do other things, right? But you got to do something. You will get 400 errors when you have too much. So you got to fix that. I also didn't spend any time on like, how do we do tracing? Like tracing is easy, I didn't have time. I wanted to show primitives. Why would you want to do a trace? To see if it did a good job. I didn't even talk about prompt tuning. There's a whole science on tuning for expected outputs, using LLMs as judges, and then feeding those back into its systems. I didn't talk anything about fine-tuning or distillation for improvement. I didn't talk about how to choose a model or even how to get these things to operate things on their own, which they can do. But hopefully this was helpful. 9 sort of tips from agentic primitives all the way to the end. Thank you so much for your time.